Yeah, so my talk is about fuzz testing Swift packages, and in particular, I'm going to propose a new way, new experimental way to fuzz test Swift packages. But before we get into that, let's ask, what is fuzz testing exactly? So it's a software technique that works by throwing many arbitrary inputs to a test function and then ensuring that it works in all cases. So in code that would look like this, in a loop that might run for hours, days, or even weeks, just constantly generate inputs and then feed them to the test function. And the kinds of functions that you might want to test are maybe simple wrappers around other functions that always return true. In this case, it only tests that the function doesn't crash, which is a useful thing to test, I believe. But it also might be a little bit more complicated. It might test that some property of the output of the function holds. For example, for a sorting function, you might want to check that the output is indeed sorted. And if this function returns false, then that means that the inner sort function is not correct. And last year, at this conference in Berlin, Jack Flinterman talked about a fuzz tester for Swift called SwiftCheck, which just helps you write these property-based tests and helps generate arbitrary data. And that's very, very interesting. I think you should watch the talk. But today, I'm going to talk about a different approach to fuzz testing. And it's an approach that's mostly used by people writing parsers or compilers. It's also used by security researchers to find flaws in low-level, mostly C programs, unsafe programs. And I'm talking specifically about tools like libFuzzer. So I'll first explain what libFuzzer is, how it works, and then we'll see that while libFuzzer is great, it has some flaws or inconveniences that could be fixed by adapting it to Swift. So we'll see how to make it more Swifty. And then finally, because it's a functional Swift conference after all, we'll see how fuzzing is really, really effective and becomes much more useful when it's used with functional programming. So what is libFuzzer? libFuzzer is a tool written in C++. It's an LLVM project, and it's a fuzzing engine. So it's a tool that can help you generate inputs to feed to a test function, ensuring it always succeeds, etc. But it has a few peculiarities. One of them is that the data that it generates, the input type, is a bit string. It's just a sequence of ones and zeros. And also, the function that it has to test is a C function that has to have this specific name, LLVM fuzzer test1 input. And if you were to write it in Swift, it would look like this. It's a function. It takes an unsafe pointer as argument and a size and returns an integer. It's a bit ugly, but it works. Why do people use libFuzzer? What makes it special? Why does it work? And that's because of the way they generate these bit strings, the way it generates these inputs. And so now I'm going to explain the algorithm that's behind libFuzzer, or at least the algorithm in broad strokes. So libFuzzer is a coverage-guided evolutionary fuzzer. And I'll explain in detail why that is. But the most important idea behind libFuzzer is that to generate new inputs, it's better to create them by mutating inputs that are already known to be interesting. So if you have some input that you know is really interesting to test, and then you mutate it slightly, then it's really probable that this new input is going to be interesting itself. But then, and also, remember that the input type is a bit string, so by mutating, I mean just bitwise mutation, things like flipping a bit or swapping 2 bits, like these little modifications. That raises the question of what is an interesting input. And the way libFuzzer scores an input, the way libFuzzer rates the interestingness of an input is based on the code coverage that results from running the test function with that input. So an input that's interesting is one that causes the test function to reach many blocks of code It's one whose code coverage is unique, and it's also an input that is small. An input that's uninteresting is, well, the opposite of that. And that means that we have to have a way to measure the code coverage that results from running the test function. And to do that, at compile time, we need to instrument the program somehow to record its code coverage. And we can do that with a tool called LLVM sanitizer coverage. So in code, that would look like this. We have that pool of inputs rated, sorted by their interestingness. We select a high-ranking input from that pool, and then mutate it slightly, feed it to that LLVM fuzzer test1 input function, analyze the code coverage that results from that function. We get back a score that from that analysis, and then we add the input along with its score back into the pool, and repeat that again and again, millions of times. And that really works. I'd like to show just a quick example of a function that would be impossible to test effectively by just throwing random data at it, but that libFuzzer is really effective at testing. And it's kind of a dummy function. It just checks that the first bytes of its inputs are exactly these values. So it has to find 64 bits, I believe. So if you count, that's billions and billions of values. You could just never find that value by chance. But if you ask libFuzzer to test that function, it will find the problematic input in less than a second. And that's because it knows that if an input reached the 6th condition, for example, it's much more interesting than an input that reached the 1st condition. So it's going to build upon that, mutate the one that reached the 6th condition, and maybe find one that reaches the 7th in that way. It goes on. And I think it takes 1 million iteration to find it in general. So that's really, really powerful. It works. But it's also a bit inconvenient. And that's because libFuzzer is not really integrated into SwiftPM. So if you want to use it in a real-world project, well, that's difficult. It's cumbersome. You'll probably have to make many modifications to your process. But you can work around that. One much more fundamental flaw, well, flaw is a bit harsh, but one thing that could be improved is that the inputs that libFuzzer generates are just bit strings. They're untyped. It generates ones and zeros. But the functions that we want to test often accept structured data. They have these really precise types that we like to work with. And so what that means in practice is that in the test function that we ask libFuzzer to use, we're going to have a decoding step, something that translates these ones and zeros into the structured data, this typed input. And that's bad for multiple reasons. First, it's slow. The decoding step, it adds a little bit of time. But also, this decoding step might fail. Maybe some bit strings don't have any corresponding typed value, and so we're just wasting cycles. And the bitwise mutations that libFuzzer use, things like flipping a bit or copying a substring, might not result in a meaningful change at the level of the typed value. And what that means is that there's really a fundamental mismatch between what libFuzzer works with, these bit strings, and what the test function works with, this structured data. And what that means is that for a lot of functions, libFuzzer will just be very, very ineffective. But I think that we can fix that by adapting libFuzzer to Swift. So what if we wrote a libFuzzer-like package in Swift, so keep the same coverage-guided evolutionary algorithm. And I just realized I didn't really explain why it was called coverage-guided evolutionary. Evolutionary just refers to the practice of keeping a pool of interesting inputs and creating new ones by mutating them, and coverage-guided because it uses code coverage to rate the inputs. So anyway, we're going to write a libFuzzer-like package in Swift, but then change the argument type of the test function so that it no longer accepts a bit string. It's no longer something that works on binary data. Instead, the test function will now be generic. It's just going to be a function from T to bool. And that solves the mismatch I was talking about earlier. But it does introduce a few new problems. in that when we were working with bit strings, there were a few things that we could get for free. For example, we knew the size of the input, so we knew how complex it was. Now we don't know the complexity of the input of type T anymore. We also don't know how to save an input of type T to a file. And more importantly, we don't know how to mutate an input of type T. The bitwise mutations that work with bit strings are not applicable anymore. And so all of these things will have to be provided by the user. And that's kind of the compromise that we have to make to improve upon libFuzzer. And the interface would look like this. The test function is now a regular Swift function that accepts anything. In this case, it's called input. Then we would have this, what I called input generator, which is basically this value that tells how to judge the complexity of an input, how to save it to a file, how to mutate it. And then the fuzzer would be this generic type that you can specialize over the type of the input generator, and then you pass it the test function as a regular closure, and the input generator, and then it starts the loop, and maybe for days, weeks, until it finds a crash. And when it finds a crash, it saves the input, the JSON encoded input, into a file. All right, so let's see an example of maybe a program, a test function that would be really difficult to test either by throwing random data at it or even by using libFuzzer. I'm going to try to find a specific graph data structure that looks like this. It has 8 nodes and I think 7 edges. And in code, it would look like this. It's just 23 conditions on the graph data structure. It has found 8 numbers, 8 arrays. Yeah, I'd just like to show how to use this adaptation of libFuzzer to Swift to find an input that is problematic for that function. So the first thing I'll show is, oh wow, this is small. Yeah, the main Fuzz test. Is this big enough? As you can see, I didn't lie to you. These are all the conditions that need to be satisfied in order for the function to fail. And then we create this generator that I was talking about earlier. Not really get into how to create it. That's scary. And then launching the fuzzer with a test function and the generator. Now, maybe more interesting is the package.swift file of this package. Because remember, we need to instrument the program such that we can record its code coverage. And so let's look at the package.swift file. It has products, dependencies on this fuzzer on my computer called fuzzcheck, list of targets. And then I added an additional argument called fuzzed targets. And what that's going to do is look at the targets named these and add instrumentation such that we can record their code coverage. It's useful to do because now we don't have to instrument every target of the Swift package. In particular, if we were to instrument the fuzzer itself, a lot of things would break. So that's necessary. In this case, we're only instrumenting the Fuzz test itself and the graph library. In order to run it, and I forgot to open a terminal, but okay, sorry. Let's make it bigger. So in order to run it, we'd use this modified version of the Swift package manager, say to build the product fuzzcheck, and then pass this configuration option called fuzz release. So we compile it, actually compiled it earlier, so it's very fast. And then you can launch this tool called fuzzcheck tool and pass it the target as argument. And then when I do that, it's going to try to find the input that causes the crash. Fun fact, this process is not deterministic. And there's also a huge variance in the time that it takes to find the input. So let's hope that it's quick. It's going just to print updates about the number of inputs that it found, the total code coverage they detected, and a few other things. And let's just wait until it finds something. I think it should be fast. Yeah. So there it found a test failure. found test failure after 1,319,000. I know, it's a big number. And then save the test failure as a certain file called test failure, and then the hash of the input to EAD. We'll look at what it looks like to EAD. Yeah, so it's a JSON encoding of the graph that we were looking for. And that's how this fuzzer works. OK, so maybe let's recap. First, we saw what a fuzz tester was, and then saw the tool called libFuzzer, which used this coverage-guided evolutionary algorithm. And I showed two functions that were really well suited to be tested with these fuzzers. But you might be thinking, well, it's like these are not the kinds of functions that are representative of those I want to test in the real world. Like, is this actually useful in real life? And the answer to that is yes, especially if you use functional programming. And the reason for that is simple, is that only pure functions can be tested. That means that the same arguments must always yield the same results, and that no side effects are allowed. But on the bright side, if everything is a pure function, then everything can be tested. And what I'd like to show now is that if we have a way to model the behavior of an app as a pure function, then we can, in a way, first test the entire app itself. And the first test would consist of simulating the user opening the app and then doing a bunch of things on it, tapping that button, typing something, searching for something, and then closing the app. And that is possible if the app is written with the Elm architecture. So as a reminder, an app built with the Elm architecture is roughly an app with 4 components. There's a state of the app, which is this simple value type. Then there's another value type called action, which is the type of a user action, such as tapping the back button, taking a photo, something like this. Then this update pure function that describes how the state of the app must evolve following a certain user action. And finally, this view function that describes the interface that should be rendered for an app with a specific state. Now, this view function doesn't actually render the interface. It just describes the interface that has to be rendered for later. But of course, it's not really possible to write an entire app using only pure functions and value types. It has to interact with its environment. It has to have some side effects. But all this stuff, rendering the interface and interacting with the environment, would be managed by a driver that's provided by this Elm framework. And what's really nice is that if we have this driver that's the only thing responsible for rendering the interface and communicating with the environment, it's possible to configure it in such a way that it doesn't actually render the interface. And it's possible to configure it such that we give it a fake environment. We mock the environment such that, in fact, the driver behaves like a pure function itself. We've eliminated all side effects from it. And once we do that, then it really becomes possible to first test the app. The test function would look like this. Its argument is just a list of user actions that should be executed after launching the app. And then we create a driver, say, don't render the interface, and use this fake world, fake environment instead of the real one. And then for every user action, just run it and see how the state of the app evolves. And after all these actions, we could just return true. In this case, it just tests that the app didn't crash. Or we could also run some tests on the state of the app, check state consistent. I'd like to show an example of that working now. And sorry, I didn't prepare like a full graphical user interface app, but I did prepare a command line app written using the same architecture. And you'll just have to believe me that it could be ported to a graphical example. And the app is just like a simple app that manages lists. So you can add an item to a list, say add make crepe, add buy milk. But you can also edit an existing item. So say edit the item with the identifier of 1. Then add dependencies between them. So in order to buy crepe, make crepe, I have to buy milk. Go back to the main screen, remove an item. All these really basic actions that work on a list of items. And I'll show what it looks like in code. So It's really small. I can't really see the files, but I think it's up. OK, so the app state is two things. The interface state, which will be like the main screen or editing a certain item. What do we show? And then a list of items. And an item is an ID, a title, and a list of dependencies. So that's for the state of the app. Interface state, list of items. And then for the user actions, there are a bunch of things: adding an item, removing an item, going into the edit view for an item, all these things. I can also show you the update function, just a mutating function on the app state. Don't pay attention to this. And then for every kind of action, how does the state of the app evolves? And then, so that's the app. That's the code for the app. Now I can maybe show you the first test. And actually, before I show you that, I'm going to start the first test now because it's going to take a while. And then I'll explain while it's running. So okay, so it's running. I'll keep explaining. So let's look at the first test itself. First, I'm creating the driver. It is basically what I showed on the slide, but in real life, it's a bit more complicated. That is 2 arguments. But just trust me, it's the same thing. And then for every user action, run it through the driver and return true, meaning, yeah, just check that the app never crashes. And then we launch the fuzzer with the test function and the generator for the list of action. OK, so now let's see how the fuzzer is doing. It's still running. OK, it found something. It found a crash just now. We're going to look at it. And I hope that it's a really complex crash. I don't know what it's going to look like. But if it is really complex, I'll show you another feature of the fuzzer that we kind of get for free, which is how to minimize an input. So the crash is the file is 42AE. 42AE. OK, so the input file that I found is just a list of user actions that have to be taken to reproduce the crash. So add an item, remove an item, go back, remove an item, edit an item, add the dependency, etc., etc. It's quite long, so I don't want to debug that. That's going to take me a lot of time. What I want to do instead is just give this file back to the fuzzer and say, OK, that's great, you found a crash, but now could you please find a smaller crash? So it's going to use the exact same algorithm. Actually, there's 2 differences. It's going to use the same algorithm, but it's going to put a complexity threshold on the inputs that it generates, such that it's only going to try to generate inputs that are smaller than the one I give it. And it's also going to hold that crashing input it's going to treat it as a special value that should be used for the source of new inputs more often. So to do that, I use the same thing, but I say should minimize it, and the input file is this. Then it's going to run and minimize the input as much as it can. That can take quite long, too. But I can look at what it achieved so far. I think it was up. It found a smaller crash and gave it this name, 6AA something. So you can already look at this. Yeah, I think I actually found the minimal test case already. So let's just stop, see what it looks like. It just minimized the input that caused the crash to its minimal form. The steps to reproduce the crash are adding 2 items, then editing the second one, adding 2 times the same dependency, then going back, removing an item, and show the dependencies for the other one. So I've put it there to make it clear. Yeah, these are all the steps that have to be taken to reproduce the crash. And the bug was that it was allowed to add duplicate dependencies, and when I was trying to remove them here, it would only remove 1. And so there would be this ID that shouldn't exist in the list of dependencies. And so that was how to combine a coverage-guided evolutionary fuzzer with a functional approach to creating apps to test an entire run of the app automatically. And yeah, so to recap, so our first tester app, libFuzzer, how to adapt libFuzzer to Swift, how to combine libFuzzer and functional programming. And the thing that I really like about this is that it really combines different worlds in a way. The world of like low-level programming and security researchers with high-level programming and apps, but and it kind of breaks boundaries. We see that by giving something stronger types, in this case, the test function stronger types, we're able to just create better tests. There is no conflict between them. And the last point I want to make is that Swift is really an ideal language to create fuzzers and to run fuzzers in. And that's because, in a way, it's a low-level language. It's built with LLVM, so it's very easy for a program to live analyze its own code coverage and respond to it. But it also has a very strong type system. That allows us to write these generic test function and to formalize the requirements for an input to be first testable in the protocol. And also, by using a Swift type system to create very precise types, it kind of reduces the space of possible inputs for the test function, and that makes the task for the fuzzer much easier. The culture around Swift really values pure functions and immutability. A result of that is that there's just more code to fuzz test at every level. It could be the entire app or just a certain function that the app uses. And finally, it has a good package manager, and that makes it possible to distribute fuzzers really easily as regular packages instead of shipping them with a compiler. And I think it's a really interesting idea, and I think I hope that more fuzzers will be developed in the coming months, years. There's a lot to research. There's a lot of problems to figure out, but I kind of glossed over. Multi-threading is an issue, and a lot of other things. Efficiency. I've tested my fuzzer in the range of minutes, but maybe after days it kind of breaks down. So there's a lot of things to test, a lot of things to empirically research, but I think it's just really exciting. Thank you. Okay, yeah, good question. So the question was, when the fuzzer generates these inputs, how does it avoid generating invalid inputs, right? The first solution is not to avoid it. And that's going to waste a lot of cycles, but it still kind of works. And the other solution is, as you said, to embed these rules in the generator itself. Yeah. So in this case, I kind of cheated a little. Like the generator only generated IDs from 0 to 10, because I don't think it was useful to generate an ID that was in the range of billions. But the logic for generating an input could be more complicated. And in a way, you can kind of like embed your own knowledge of the app into the generator. And that gives another source of knowledge for the fuzzer to use to generate these inputs. Yeah, Brandon?
Awesome. So I have, I guess, a multi-part question. How long did it take you to write the Swift version of this? And how much do you delegate to the underlying fuzzer, or how much of that logic could be implemented in your Swift?
Right.
And I guess that's
So the question is, how long did it take me to write the fuzzer, and how much I delegate to libFuzzer, right? I don't use libFuzzer at all. Just a re-implementation entirely. The algorithm actually changed a little too. And how long? I don't know. I worked a little bit on it for a few months. Sometimes intensely, sometimes less intensely. Yeah. So the question is, what are the requirements to run the first test, right? So you have to keep in mind that it's a really long-running process. If you were to use it in an XC test, then a single test case would run for days, and you would just never get to the other ones. I think it's just really better to put it in a CI, forget about it, and run multiple instances in parallel. And I'm really not sure how it could be integrated into XC test case, mostly because I don't know that much about XC test case. The requirements, well, you have to create a new program that launches that fuzzer, right? So in the Swift package, just create a new target and make it depend on first check and compile it with the instrumentation that's needed. I think these are the only things to run it. Does that answer your question? Or
do you need to modify the compiler?
Yeah. Well, you need to modify the Swift package manager such that it knows which target to instrument. But the thing that instruments the program itself is built into Swift. So it's the Swift C, the compiler, knows how to add these hooks to analyze the code coverage. But the Swift package manager doesn't know how to limit like that configuration option to only a few targets. Yeah.
Your apps within your functions, and you combine that with like crashes collected from production, you could use the data to identify the initial space of crashes, and then you can write the minimums using fuzzer to find this like minimal crashing cases. And like that, running in sequence with somewhere on CI, you can keep your engineers
Well, I'm sorry, I didn't hear the end. Could you speak up a little bit?
Yeah,
I didn't hear the end. Could you speak up a little bit?
So basically combining crash production from production with app with your state.
Oh yeah, definitely. Yeah. So the comment was that you could combine this architecture, the ALM architecture, to kind of record crashes in production and then feed them to that fuzzer to find a minimal test case. And I think, yeah, that's a good idea. Maybe some privacy implications in just recording every action that the user takes. But the idea is nice. You could do it for beta apps. Yeah?
Did you submit your changes to the SPM, to the repository?
The question is, did I submit my changes to the SPM repository? No. I'm not sure that the interface I chose is right, or the implementation is right. It's just more of a proof of concept. Yeah. Oh, yeah, there. Yeah.
Do people use fuzzers for UI testing? Because like, I feel like a source of a lot of unknowns might be like gestural rather than...
Right. I don't want to say, so the question is, do people use fuzzers for UI testing? I don't know. I don't want to say no, but I don't know of any. If someone knows the answer. Yeah?
I've heard of people doing that, like leaving an iPhone running for a very long time, like automatically cooking things so you can go around, and if it eventually crashes, you found yourself trapped in fuzzing, basically.
Yeah. Oh, thank you.